On October 20th, 2025, the world stopped breathing. Phones froze mid-scroll, smart homes fell silent, and screens that had never gone dark before suddenly blinked out one by one. From Virginia to Seoul, data centers that form the invisible skeleton of modern civilization began collapsing in on themselves like neurons misfiring in the global brain. And almost at that same moment, far beyond the reach of satellites or signal, an interstellar visitor named 3I Atlas slipped behind the sun and vanished from every telescope on Earth. 2 disappearances, one digital, one cosmic. Coincidence or choreography? The timing was so perfect it felt scripted. The largest cloud network on the planet, Amazon's U.S. East region, failed without warning, taking down everything from banking systems to social media. Within 24 hours, astronomers lost sight of the only interstellar object currently inside our solar system. 2 blind spots opened simultaneously, one in our technology, one in our sky. If you're watching this, you probably remember that day. The quiet hum of the internet, something you never think about, was suddenly gone. Snapchat, Fortnite, Alexa Ring, all of it frozen. Your digital heartbeat stopped. But here's the part that nobody wants to talk about. The same week that your apps went dark, the universe did too. 3I Atlas isn't just another comet. It's one of only 3 confirmed interstellar visitors in human history racing toward the sun at more than 100,000 miles per hour. For months, astronomers had been tracking it obsessively, taking measurements, analyzing spectra, arguing over its strange chemical makeup. Then, just as it reached the most critical point in its journey, the moment it swung closest to the sun, it vanished behind that blinding glare. From Earth's perspective, the object entered what astronomers call solar conjunction, a period when the sun blocks our view completely. That blackout was expected. What wasn't expected was that it would happen at the exact same time our own network civilization went blind. The engineers at Amazon called it a cascading failure. DNS resolution failures, corrupted monitoring systems, database endpoints that stopped responding. Every layer of automation designed to prevent collapse failed in perfect sequence. Meanwhile, astronomers were watching their own systems fail not from malfunction, but from geometry. The object simply disappeared. 2 different kinds of blindness unfolding side by side. Now imagine that. Humanity's 2 main senses, the digital and the cosmic, both flickering off in the same 48-hour window. Our servers went silent, our telescopes went dark, and for a brief moment we were deaf to both ourselves and the stars. That's crazy, right? And yet it happened. It doesn't matter whether you believe in patterns or pure coincidence, the timing alone forces a question. How fragile are our senses? How many of the systems we depend on could fail simultaneously without warning? Think about it. Every photo, every message, every financial transaction, every satellite ping, all of it flows through infrastructure built by a handful of companies. And every piece of data about our universe depends on a handful of instruments pointed at the sky. We've built a civilization that runs on observation, but we rarely stop to ask what happens when the observers can't see. Maybe it was all chance. Maybe it was nothing more than bad timing. But the overlap revealed something important. Both our technological systems and our cosmic monitoring share the same vulnerability. They depend on continuous visibility, and both can go dark in an instant. So tonight we're going to follow that trail, from the power grids of Northern Virginia to the orbit of a comet no human will ever touch. Because whether you're looking up or looking down, this story isn't just about astronomy or engineering, it's about awareness. about what happens when the lights go out and we realize how much of our world exists only in the glow of a screen or the reflection of sunlight off a distant object. If stories like this make your mind race, don't just stay in the shadows. Hit like, subscribe, and share this video so you're on the front line as this investigation unfolds in real time. Drop a comment with where you're watching from and whether you think this was coincidence or something more. Because what we found next will change how you see both the internet and the universe itself. The first thing you noticed during that blackout wasn't silence, it was confusion. Your phone still showed full signal bars, but nothing loaded. The Wi-Fi icon blinked like a dying heartbeat. Your smart speaker stopped answering questions. The systems we built to feel permanent suddenly felt like ghosts present but unreachable. And for the first time in a long while, humanity felt what it was like to be disconnected from itself. Inside Amazon's data centers, engineers were staring at cascading red alerts, flooding their dashboards. The failure began in a single region, U.S., East 1, Northern Virginia, the nerve center of the global web. Within minutes it spread across continents, toppling everything that depended on it. Banking APIs, rideshare networks, airline check-ins, even the servers that stored system status pages meant to explain what was happening. It was a digital Ouroboros, a self-devouring loop. For most of us, it felt like a bad day online, but for those who understood the scale, it was a civilization-level event. Half of the global internet depends directly or indirectly on 3 cloud providers. One of them had just fallen asleep at the wheel. Every router that failed, every heartbeat packet that went unanswered, reminded us that the web isn't a cloud at all, it's a chain, and chains break. Meanwhile, up above that chaos, the other kind of darkness began. Observatories pointed toward the sun, reported the same sentence: Atlas is gone. It wasn't destroyed or vaporized. It was simply hidden by the glare slipping behind the solar curtain, where no telescope on Earth could see. A cosmic outage timed almost perfectly with our technological one. Now, coincidences happen all the time. But the more researchers compared the timestamps, the more eerie the overlap became. The AWS incident started at 9:42 a.m. Eastern Time. Solar conjunction reached its peak at 9:57, 15 minutes apart. 2 different systems, one human, one cosmic, both blind at once. That's not to say they were connected, there's no evidence of that. But the symbolism hit hard. A species that built machines to connect everything suddenly found itself cut off from both the digital world and the stars. We weren't just offline, we were out of sight. You might think of the internet as a convenience, but it's more like an organ. It regulates commerce, communication, power grids, even emergency services. When that organ stops, everything downstream suffocates. In less than an hour, planes were grounded, hospitals switched to manual protocols, and global stock markets froze in place. The same kind of paralysis astronomers experience when the sun blinds their instruments, waiting for the light to shift, praying they didn't miss something crucial. What makes this truly unsettling is how similar those 2 blind spots are. Both exist because of dependence. The internet depends on centralized servers. Astronomy depends on clear lines of sight. Take either away, and the whole system collapses. We've spent decades layering technology and telescopes to expand our awareness, yet both can vanish in the same instant, proof that progress doesn't always mean stability. And here's where it gets personal. Think about your own dependence. How many of your memories, photos, or conversations live only in the cloud? How much of your curiosity about the universe depends on screens and sensors? When those go dark, who are you? What do you still know? The blackout was a warning disguised as inconvenience. A glimpse of what happens when the lights flicker and we remember how fragile connection really is. Scientists scrambled to bring their telescopes back online, engineers rebooted databases, and by the end of the week, everything seemed normal again. But deep down, everyone knew something had shifted. We saw how easy it is for the modern world to vanish first digitally, then cosmically, and that's a pattern worth paying attention to. Because the next time it happens, it might not just be a glitch. It might be the moment we realize that the universe doesn't owe us visibility, and that blindness, whether caused by sunlight or server logs, might be the natural state of things. In the hours that followed the blackout, the internet slowly began to recover, but the sky didn't. Engineers rebooted their servers, rebuilt routing tables, and the digital world blinked back to life piece by piece. But above that fragile recovery, the universe stayed silent. Astronomers around the world were still blind. Atlas, the interstellar visitor, was now hidden completely behind the sunday. Every telescope that tried to track it reported the same thing, a blank field of light. At first, nobody thought much of it. Solar conjunction happens all the time. When an object moves behind the sun from Earth's point of view, it disappears until it emerges again on the other side. But this time, something about the timing felt off. For months, Atlas had been showing faint but measurable activity, jets of gas, subtle variations in brightness that hinted at a complex internal structure. Then, just as it reached the most critical phase of its journey, it vanished, and so did our ability to record it. One astronomer from the Pan-STARRS Observatory said it best. It's like watching a magician toss a coin into the air, then someone turns off the lights before you see where it lands. When the lights came back on, would Atlas still be there? Would it look the same, or would it somehow be gone for good? For a few restless days, the scientific community debated how to fill the void. Data teams created models predicting what the object might be doing behind the sun, whether it was breaking apart, changing trajectory, or interacting with solar radiation. Some even speculated that it might have already disintegrated and that we'd never see it again. But that theory didn't sit well with others. There was no evidence of debris, no signal, no trace, just absence. Meanwhile, deep in a monitoring lab in Maryland, a group of researchers noticed something strange in satellite telemetry. A handful of instruments designed to track solar wind fluctuations recorded an unusual dip in radiation pressure during the same window when Atlas disappeared. It wasn't dramatic, barely outside the range of normal variation, but it was enough to raise eyebrows. Something had changed near the Sunday. The data didn't prove anything, but it whispered. And this is where things start to blur between coincidence and narrative. The engineers who'd spent the week fixing internet servers were now watching the astronomers struggle to reconnect with the cosmos, and both groups were asking the same question. How much of what we see is real, and how much is just visibility? If our tools define our perception, then losing sight isn't just a data gap, it's a loss of awareness. That realization hit hard. We talk about exploration like it's a straight line, but it's not. It's a flicker between seeing and not seeing, knowing and guessing. Every mission, every telescope, every probe is a fight against darkness, and sometimes the darkness wins. Atlas's disappearance wasn't just another solar event, it was a reminder that the universe still holds the power to silence us. By the end of the week, headlines had already moved on. AWS was back online, flights resumed, social media returned to endless scrolls. People stopped thinking about that eerie overlap the day the internet and the universe both went dark. But in the quiet corners of research institutes, a few scientists couldn't let it go. They noticed a pattern in the noise, a faint echo between the datasets. Something that suggested Atlas's vanishing act might not have been the end of the story, but the beginning of something stranger. Because sometimes when everything goes dark, it's not because the light has disappeared, it's because something new has stepped into its path. Inside the observatory control room, the light from dozens of monitors painted everything in shades of blue and gold. Scientists leaned over keyboards, whispering numbers, their faces illuminated by data instead of daylight. Atlas had vanished behind the sun days ago, and every hour that passed without new readings deepened the unease. For the astronomers, this wasn't just a cosmic event, it was personal. They had devoted years to tracking this strange interstellar visitor, and now it was gone, swallowed by glare and geometry. Sleep became optional. One team at the European Southern Observatory pulled an all-nighter, running simulations of what might be happening on the far side of the Sunday. They modeled spin rates, fragmentation scenarios, even theoretical propulsion caused by asymmetric outgassing. None of it fit perfectly. Every new result contradicted the last. The data refused to behave. One researcher compared it to chasing a shadow that keeps changing shape. In a quiet corner, a systems engineer named Luca stared at a row of blinking error logs. His job wasn't to interpret astrophysics, it was to keep the network that relayed telescope data online. But that night, the network wasn't cooperating. High-bandwidth feeds from Chile, Hawaii, and Arizona were dropping packets at random intervals. At first, Luca assumed the issue was weather, until he realized the same interference was appearing across 3 continents simultaneously. Something in space was disrupting the connection. He didn't tell the scientists right away, he wanted to be sure. When he finally showed the logs to his supervisor, she frowned. The timestamps of the signal loss matched perfectly with a burst of solar noise detected by the SOHO satellite. It wasn't enough to cause damage, but it was enough to scramble transmission. The sun wasn't just hiding Atlas, it was drowning out its digital echo too. That realization hit like a gut punch. The very star that gives us light was also the reason we couldn't see what lay beyond it. The universe has a sense of irony that feels almost human. The more light we chase, the more blind we become. As the hours turned into days, the mood shifted from anxiety to reflection. In between calibration checks, the scientists began talking not about data, but about perspective. Someone mentioned how ancient cultures once feared solar eclipses as omens, moments when gods turned their faces away. Someone else said maybe that fear never really left us. We've just replaced superstition with science, and the awe feels the same. It's strange to think about, but even now in the 21st century, our ability to see the cosmos depends on geometry and luck. If a single angle changes, if a single orbit misaligns, we lose sight. Entire worlds can hide behind the sun invisible, not because they're far away, but because of where we happen to be standing. For all our telescopes and satellites, we're still a species trapped on one side of a flashlight beam, staring into glare and calling it knowledge. Down the hall, Luca watched another data relay flicker and fail. He smiled, exhausted, and muttered, maybe the universe just needs privacy. It was a joke, but it carried a truth that none of them could shake. The more we connect, the more the cosmos reminds us that connection is conditional. And somewhere beyond that brilliant wall of light, Atlas kept moving, unseen, unmeasured, maybe unchanged, or maybe not. The question that haunted every lab wasn't whether it would return. It was whether when it did, we'd still recognize it. If you've ever wondered how close you are to the heartbeat of the universe, it turns out you can check it yourself. That's the crazy part about modern science, it's not locked inside labs anymore. You can watch the same satellites, read the same data, and even see the same cosmic blind spots that NASA scientists stare at. All you need is a browser and a bit of curiosity. Start with NASA's real-time dashboards. They're public. You can open the Solar System Dynamics page and see exactly where 3i Atlas is supposed to be, even though it's currently hidden behind the Sunday. You can check the Deep Space Network's live telemetry streams, the same system that tracks spacecraft millions of miles away, and watch for the moment Atlas re-emerges from solar conjunction. It's like peering through the universe's closed eyelid, waiting for it to blink again. And if you want to trace the heartbeat of the digital world, there's the AWS Global Status page, Cloudflare's network map, and the Space Weather Prediction Center's live geomagnetic activity feed. Every one of them is a window into the pulse of our civilization. The colors on those maps, the red spikes, the orange zones, the faint lines tracing cable routes, those are the modern equivalents of heartbeat monitors for a planet connected by light. What's wild is that you can see how fragile it all really is. Watch the AWS dashboard long enough and you'll notice how often small disruptions happen. A blip here, a delay there. Multiply that by thousands, and you begin to understand how close we are to the edge every single day. The same goes for space observation. Even a small solar flare can wipe out telescope readings for hours. A few degrees of orbital alignment can make entire regions of space invisible. The system works beautifully until it doesn't. That's what makes this moment so powerful. Because for once, science isn't just about experts telling you what they found. It's about showing you how to look for yourself. You don't need a PhD or a telescope. You just need perspective. Open your laptop, zoom out on the solar system model, and realize that every glowing dot, every invisible trajectory is part of the same fragile network that runs through your own devices. When the internet went dark and Atlas disappeared, those blind spots overlapped perfectly. But that alignment also gave us a mirror. It showed that fragility isn't failure, it's the cost of complexity. The fact that you can even monitor this from your couch on a glowing rectangle of glass is proof of how far we've come. Still, there's something humbling about it. You can watch the dashboards update, you can see the lines reconnect, but you can't stop the sky from hiding what it wants to hide. You can predict when Atlas will reappear, but you can't force the light to move faster. You can refresh the page all you want, but the universe doesn't run on your schedule. And maybe that's the lesson hidden in this entire event. We've built a civilization that lets you see everything except the limits of your own sight. You can witness a global network flicker back to life, or track an interstellar visitor orbiting the sun, but you can't escape the truth that both systems, technological and cosmic, are running on borrowed visibility. One storm, one glitch, one shift in orbit, and you're blind again. So go ahead, pull up the dashboards, the trackers, the maps, watch the universe in real time. Because the next time the lights flicker, you'll know exactly what you're looking at and what you're not. If there's one pattern the universe never breaks, it's repetition. Every collapse, every blackout, every moment of blindness eventually circles back as revelation. The same week the internet crashed and Atlas disappeared, humanity got a rare mirror held up to its own design flaws. We build systems to see farther, connect faster, and know more, but we rarely build them to fail gracefully. And that more than anything might be the real story here. When the internet came back online, it didn't come back stronger. It came back familiar, humming along as though nothing had happened. The dashboards turned green again, headlines moved on, and the outage was chalked up to a rare technical cascade. But underneath that tidy explanation was a truth that couldn't be patched. The digital world isn't resilient, it's recursive. The more we depend on it, the more we trap ourselves inside it. The same is true for astronomy. Every telescope, every satellite, every detector is a way of extending our senses. But those senses are fragile. They depend on geometry, timing, and clear skies. The moment Atlas vanished behind the sun, our vision failed, not because our technology was weak, but because it was human. Built with limits, bound by physics. And maybe that's the point. We like to imagine progress as infinite, but progress is just another form of balance. We push forward until the system reminds us that seeing everything is impossible. Even gods, if they exist, must have blind spots. Maybe that's what connects us to them. Think about it, our two greatest tools for understanding reality, data and light, can both disappear in an instant. One glitch, one solar flare, one corrupted packet of information, and the illusion of control collapses. Yet every time we rebuild, every time we reconnect, we convince ourselves the system is permanent again. It's not, it's just awake for now. There's something strangely comforting in that. Knowing that fragility isn't a flaw, it's a heartbeat. Systems that never break stop growing. Observers who never lose sight stop discovering. Maybe the blackout wasn't a failure at all. Maybe it was a cosmic reminder that awareness only matters when we know what it feels like to lose it. You felt it too, didn't you? The moment your phone froze, the second you realized the world had gone quiet. That instinctive panic wasn't about missing messages, it was about losing visibility. It's the same fear that drives astronomers to chase light across galaxies and engineers to rebuild servers at 3 a.m. The fear of not knowing, the fear of the dark. But here's where it turns poetic. Darkness isn't the opposite of connection, it's the space that gives connection meaning. The night sky needs its black canvas so stars can exist. The internet needs downtime to remind us it's alive. And maybe, just maybe, we need moments like this to remember that sight isn't everything. Understanding begins in blindness. So the next time you refresh a page that won't load or glance at a star that suddenly disappears, remember this week, the week humanity blinked. The moment when the internet and the cosmos both went dark, not to punish us, but to remind us what light actually means. Because fragility in the end isn't weakness, it's proof that the system is still alive. When the lights came back on, the story shifted underground to the cables, routers, and server farms that make up the invisible body of the internet. You've heard the phrase the cloud so many times it almost sounds mythical, but the truth is brutally physical. The cloud lives in warehouses, in metal racks, humming with heat in vast rooms cooled by fans the size of airplane engines. It's not floating anywhere, it's wired, heavy, and alive. In the hours after the blackout, Amazon's engineers began dissecting the collapse. The epicenter was one specific region, U.S. East 1. If the internet were an organism, that region would be its heart. Thousands of companies rely on it, streaming platforms, payment processors, hospitals, airlines. When it stopped, everything downstream suffocated. The failure began with a subtle misfire in the system that manages how different parts of the network talk to each other. One misrouted command spiraled into chaos, creating a traffic jam of digital signals so dense it choked its own arteries. You'd think a network this advanced would have redundancies, backup systems ready to take over. It does. But here's the paradox. The same automation designed to protect it also became the problem. Scripts that were supposed to reroute traffic began rebooting themselves repeatedly, each restart spawning new errors. Engineers called it a looping cascade. Imagine an entire nervous system trying to heal itself, only to trigger more pain. That's what digital fragility looks like. It isn't dramatic sparks or explosions. It's quiet recursion. A machine arguing with itself faster than any human can intervene. By the time teams noticed, the network was tangled in its own recovery code. Systems that were meant to protect the web from human error failed because they worked exactly as designed. Inside one of Amazon's Virginia data centers, an engineer later described the moment it clicked. "We realized the automation had gone blind," he said. "It wasn't seeing the problem anymore, it was just reacting." The phrase echoed what astronomers had said about Atlas the same week: the system can't fix what it can't see. As the hours stretched on, people outside the labs felt the ripple. Payment terminals stopped working in coffee shops. Smart locks refused to open. Delivery routes froze. It was like watching modern life forget how to breathe. The outage lasted only a few hours, but its shadow stretched across the week. Analysts later estimated the financial loss in billions, but that wasn't the real damage. The real damage was existential. We realized our civilization depends on an invisible network that can trip over itself in seconds. Here's the part that really makes your skin crawl. The system didn't break because of sabotage or attack. It broke because of trust. Trust in automation, trust in redundancy, trust that the machine would always self-correct. We built complexity faster than we built understanding. And when that complexity turned inward, it revealed something uncomfortable. Our technology is evolving faster than our ability to watch it. But that's not just a tech problem. It's a human one. We create systems that outgrow our sight, and then we act surprised when they go dark. The cloud collapse wasn't a fluke. It was a preview of what happens when intelligence, human or artificial, loses context. A blindness that isn't total but systemic. The same kind of blindness that happens when a comet slips behind the sunday. And that connection between the digital and the cosmic isn't metaphor, it's diagnosis. Both failures came from the same root cause: overconfidence and visibility. We thought we could monitor everything, map everything, understand everything, but the universe and our own code has other plans. When engineers later reconstructed the timeline of the blackout, they realized it hadn't been a single failure. It was a cascade, like dominoes toppling in multiple directions at once. Each digital subsystem depended on another. The authentication servers relied on the logging servers relied on the status monitors, and the monitors relied on the authentication layer. It was circular, elegant, and catastrophically fragile. The moment the first authentication cluster faltered, the dominoes began to fall. Systems that were supposed to fail independently began collapsing together, locked in a feedback loop. One engineer compared it to a spider web snapping from the center. The damage radiated outward faster than anyone could respond. Red lights lit up across dashboards around the world as data centers from Virginia to Dublin began to suffocate under their own traffic. The problem wasn't just technical, it was architectural. Modern cloud networks are built for efficiency, not separation. The very thing that makes them powerful, their interconnectedness, makes them brittle. Every optimization, every shortcut, every clever bit of redundancy becomes a hidden point of failure when stress builds. We call it a resilient system, but that phrase only means it hasn't broken yet. By mid-morning, engineers realized that restoring one subsystem required access to another that was also down, a perfect deadlock. Manual overrides couldn't help because even the control panels ran on the same infrastructure that had crashed. They were trapped inside their own dependency graph. The system wasn't just offline, it was recursively blind. In the middle of that storm network, researchers from Thousand Eyes began mapping the collapse in real time. Their visualization looked less like a web and more like a forest fire, orange and red nodes spreading across continents as traffic rerouted, failed, then tried again. Billions of automated requests bounced back and forth, hunting for servers that no longer existed. For a few hours, the world's information systems acted like a living organism, having a panic attack. If you were online that day, you felt it too. Websites took forever to load. Payment gateways froze mid-transaction. Video calls lagged into silence. The modern rhythm of life, a rhythm so smooth it feels like breathing, started to stutter. We're so used to that constant pulse of connectivity that when it skips, it feels like the world itself is sick. That sickness has a name: cascade failure. It's what happens when complexity becomes so intertwined that nothing can fail in isolation anymore. The more advanced our systems get, the more synchronized their breakdowns become. It's a cruel irony. Progress doesn't eliminate fragility, it standardizes it. Later, during the post-mortem, one engineer said something that stuck with everyone. "We didn't lose data, we lost direction." In those words was an echo of something bigger, something astronomers had said about Atlas when it vanished behind the Sunday. They hadn't lost the object, they'd lost sight of it. The digital and the cosmic were beginning to rhyme again, and that rhyme wasn't poetic, it was diagnostic. Because when systems from networks to telescopes start to fail in the same way, it's a warning. It means we're designing reality around the same blind spots. Efficiency over separation, connection over clarity, speed over understanding. And when those priorities align, collapse isn't an accident, it's a feature. When the post-mortem reports finally came out, the story was uglier than anyone expected. Engineers discovered that the entire cloud ecosystem was balanced on assumptions that had never really been tested. A single configuration service designed years ago acted as the traffic controller for half the global web. It wasn't a secret, just something everyone had quietly agreed not to think about. When that service froze, it took the rest of the world down with it. That revelation hit harder than any cyber attack could have. There was no villain this time, no hacker in a basement, no government plot. The enemy was architecture itself. The network wasn't designed to survive its own complexity. It was a skyscraper built on scaffolding that nobody remembered building. Every piece of software relied on a chain of other software that relied on assumptions written by people who had already left the company. For decades, we've treated the cloud like a metaphor for safety. The word itself feels soft, distant, safe. But clouds aren't safe, they're transient. They exist only as long as the conditions that form them. Pull away the moisture, and they vanish. The digital cloud is no different. It's just humidity made of code. One systems analyst described it perfectly. We didn't build the cloud, we grew it. That's what makes it terrifying. It evolved organically, layer by layer, without a master blueprint. Every redundancy we add makes it smarter, faster, and more fragile. The more we connect, the less we understand what we've created. By the second day after the blackout, the global network was technically stable again, but the illusion of control was gone. Regulators wanted explanations, companies demanded safeguards, and journalists wanted a culprit. But there was no single person to blame. The collapse was systemic, a side effect of how efficiency rewards shortcuts and how convenience disguises dependency. It's hard not to see the irony. We built machines to eliminate failure and ended up designing a system where failure travels at the speed of light. Every safeguard is just another dependency, another point where the dominoes can start again. The architecture of the internet is in many ways the architecture of human ambition, dense, efficient, and always one step from collapse. Here's the truth. Most people don't want to hear the phrase distributed network is a myth. What we actually have is concentrated power disguised as decentralization. A handful of data centers process most of the planet's digital life. Knock out 3, maybe 4, and the illusion of global resilience shatters. The internet isn't an infinite web, it's a handful of throbbing arteries pulsing in sync. That's why the AWS collapse felt so symbolic. It wasn't just a server outage. It was a physical reminder that the digital world we take for granted has a pulse, a heartbeat, and it can stop. When it did, even for a few hours, we all got a glimpse of how fragile our species' second nervous system really is. And yet we'll rebuild. We always do. We'll patch the code, update the systems, add new redundancies, and tell ourselves it's fixed. But deep down, we know it's only temporary. The architecture hasn't changed. The next failure is already written somewhere in the code, waiting to be triggered by a single invisible condition. It's not a matter of if, it's a matter of when. If you want to understand how fragile the modern world really is, you don't need to study computer science, you just need to know how to check a few dashboards. Everything that keeps civilization humming now lives on screens you can open from your couch. The cloud isn't mystical anymore. It's a public utility, and like any utility, it tells you when it's hurting. You just have to know where to look. Start with AWS's status page. It's the pulse of the internet. Every region, Virginia, Frankfurt, Singapore, glows in shades of green when healthy. But if one turns yellow or red, even for a few minutes, you can watch the ripple spread in real time. Banking apps start to fail, delivery services freeze, half of TikTok goes quiet. That's the heartbeat of the planet visible through a browser tab. Now pull up Cloudflare's network map. It looks like a weather radar for data. Lines trace undersea cables, nodes light up like constellations. When something breaks, the color shifts blue to orange to deep crimson. You can literally watch the internet's blood pressure spike. Next, visit Thousand Eyes or NetBlocks. They track outages across countries. You'll see how one region's silence creates echoes in another. It's humbling. We built this colossal machine to be global, but its weak points are always local. The same way a single fault in one neuron can paralyze a whole body, one data center failure can ripple across 6 continents. But this isn't just about the digital side. There's a mirror image above us, and it's cosmic. NASA's Solar Dynamics Observatory publishes live images of the sun every 10 seconds. If you've never seen it, go look. It's mesmerizing loops of fire, arcing thousands of miles into space. Every burst, every solar flare is a reminder that the same star, powering your daylight, can also fry satellites, distort GPS, and blind telescopes. The next solar storm won't just disrupt Wi-Fi, it could reset modern civilization back a few decades. So here's a challenge. Set aside one evening and open all these dashboards at once: AWS, Cloudflare, NASA's Heliophysics page, and the Space Weather Prediction Center. Watch them update side by side. You'll notice something profound: they pulse together. When the sun hiccups, data spikes. When networks overload, solar radiation readings fluctuate. It's as if our civilization and our star are breathing in sync, one digital, one cosmic. That's not superstition, it's systems theory. Everything connected is everything at risk. The web mirrors the sky more than we'd like to admit. Both are networks of energy, both capable of brilliance and collapse, both addicted to balance they can't sustain forever. And this is where the story gets practical. Because this isn't just an abstract science mystery, it's your daily life. If you depend on smart devices, if you store your memories in the cloud, if you navigate by GPS or pay with a phone, you're part of the same fragile loop. Knowing where to look isn't paranoia, it's literacy. Learn to read the heartbeat of the systems that keep you alive. When they skip, you'll feel it first. And the next time you open one of those dashboards and see a region flicker from green to red, take a second before refreshing. You're not just looking at data, you're watching civilization blink. Right now, there's something drifting through the solar system that doesn't belong here. It's small, dark, and silent, an interstellar visitor from another star traveling faster than anything we've ever launched. Astronomers call it 3I Atlas. The 3 means it's only the third confirmed object from outside our solar system ever found. The name Atlas comes from the survey telescope that spotted it. The meaning, though, feels poetic. In myth, Atlas was the titan who held up the sky. This one seems determined to challenge it. When it first appeared on observatory feeds, it didn't look like much, just a faint, elongated smudge gliding across the background of stars. But once scientists calculated its orbit, everything changed. Its trajectory wasn't bound to the sun at all. It was a hyperbolic escape route, proof it came from beyond. And that raised questions humanity isn't used to asking. Where did it come from? What is it made of? And why now? Just a few years after 2 other interstellar objects, Oumuamua and Borisov, slipped through the neighborhood. By the time Atlas drew near, telescopes across Earth and in orbit were tracking it obsessively. The data was strange from the start. It didn't behave like Borisov, which was clearly a comet shedding gas and dust in a brilliant tail. It also didn't resemble Oumuamua, which was flat and accelerated slightly as though pushed by something invisible. Atlas was something in between. It reflected light inconsistently, suggesting an irregular shape or a tumbling spin, yet it stayed eerily stable as though guided. Then came the headlines. 3rd interstellar visitor detected, Atlas the stranger from deep space. For a few weeks, it felt like the whole world was looking up again. And maybe that was fitting, because while engineers were rebuilding the digital cloud back on Earth, astronomers were realizing we'd been living in another kind of cloud, all along, the one made of assumptions about what counts as natural. That's what makes Atlas so unsettling. Every discovery about it seems to contradict something we thought we knew. For instance, its albedo, the way it reflects sunlight, is unusually high, more like metal than rock. Its rotation rate isn't chaotic like most small bodies, and some instruments even picked up faint signatures of cyanide gas, a chemical tied to both cometary activity and the building blocks of life. It's both familiar and alien at once. And yet, for all our technology, we're still watching from billions of miles away. Each pixel of data we get from telescopes represents a story we can't quite read. The object doesn't explain itself. It doesn't have to. It's just passing through. You can think of Atlas as a cosmic messenger or a mirror. It reflects not just light, but curiosity, paranoia, and everything in between. We want to believe it's natural because that's comforting, but we can't prove it. And that uncertainty is the fuel of both science and fear. Here's the beautiful irony: our digital blackout reminded us how blind we are when systems fail. Now, in the aftermath, we've discovered something that humbles those same systems. No telescope can track Atlas forever. It's moving too fast, too far. We'll lose it again soon, just like we lost Oumuamua. But before it disappears for good, it's leaving us one simple question: how do you study something that refuses to stay still? Maybe the better question is this: what if that's the point? Maybe the universe keeps sending these visitors, not to be studied, but to remind us how little we see when everything seems to work perfectly. From Earth's perspective, 3I Atlas has now slipped behind the sun, vanishing into a brilliance so intense, it turns the instruments meant to see it into blind eyes. Astronomers call this phase solar conjunction, and it's one of the few things that can silence even our best telescopes. The geometry is simple. The sun sits directly between us, and the object flooding every sensor with radiation and glare. But the effect feels anything but simple. It's like the universe pulled a curtain across the stage right before the next act. For weeks leading up to the event, observatories across the world had been watching the countdown. Each night, Atlas appeared lower in the sky until finally it dipped too close to dawn for any ground-based telescope to catch. Space telescopes held on a bit longer, but even they began to lose tracking lock. The sun's glare doesn't just wash out visible light, it corrupts radio signals, optical guidance systems, and infrared sensors. It's total sensory overload. And that's what makes this moment feel so paradoxical. The same star that makes observation possible also makes it impossible. Our vision depends on light, but too much of it blinds us. That's not just poetic, it's physics. Every form of perception, biological or technological, has a saturation point. Beyond that, information becomes noise. To work around that mission, planners rely on timing. They schedule spacecraft trajectories and telescope operations so that the sun's interference window stays as short as possible. But even then, there's an unavoidable gap. For anywhere between several days to several weeks, the data stream goes dark. The object doesn't vanish, it just hides behind the most powerful light in the solar system. If you think about it, there's something profoundly human in that. We want constant clarity, but the universe demands patience. Every observation has a blind spot built in. Every search for truth includes a moment of forced humility. Solar conjunction is nature's reminder that even the best instruments need to blink. During that blackout, astronomers keep themselves busy. They model orbital dynamics, predict reappearance points, refine light curve equations. But no one can resist checking the data feeds just in case some stray reflection sneaks through. Hope doesn't stop, because light does. Meanwhile, in those same days, something strange begins happening across unrelated systems. A handful of spacecraft experience minor telemetry glitches, noise bursts in communication channels that nobody can fully explain. Some blame cosmic rays, others call it coincidence. Either way, the timing is impossible to ignore. The universe went silent, and so did our machines. Maybe it's nothing. Maybe it's everything. What's certain is that every blind spot teaches us the same lesson: seeing is temporary. Every instrument, every eye, every sensor eventually faces a limit where light itself becomes the enemy. And that realization lingers longer than the blackout itself. Because when Atlas finally emerges from behind the sun, the first question astronomers will ask isn't what it looks like, it's whether we missed something while it was gone. For days after Atlas disappeared behind the sun, the data streams were silent. Then, almost imperceptibly, the noise began to change. Deep in a laboratory at the Jet Propulsion Facility, a young researcher named Arya noticed a pattern in the static, tiny, rhythmic modulations in the solar background that didn't match normal interference. They were too consistent, too clean. The signal was weak, buried under the roar of solar radiation, but it pulsed with uncanny regularity. At first, she dismissed it as a calibration glitch. Instruments often develop micro-patterns in noise during thermal cycles. But curiosity kept her up that night, running correlation checks. When she compared the timing of those pulses to the last confirmed trajectory of Atlas, the alignment was almost perfect. The signal seemed to echo the object's expected spin period. That finding raised more questions than it answered. Was it a coincidence, a natural resonance effect, or was Atlas reflecting sunlight in some way the models hadn't predicted? Whatever the cause, it meant one thing: Atlas wasn't gone. Even hidden behind the sun, something about it was still interacting with the solar environment, leaving a faint fingerprint of motion. When she shared the discovery with her supervisor the next morning, the reaction was cautious but electric. A few senior scientists gathered around her screen, leaning closer, as if the tiny fluctuations were whispers from another world. They decided to flag the anomaly for further analysis. The file name she chose was simple: Heartbeat. While the team began preparing for Atlas's re-emergence, conversations turned philosophical. They couldn't help comparing the phenomenon to human behavior under pressure. When we lose sight of something we care about, we invent ways to sense it anyway. Hope becomes a kind of radar. Arya's heartbeat wasn't proof of anything yet, but it reminded everyone in that room why they became scientists in the first place. Curiosity doesn't die in darkness, it adapts. In the weeks that followed, other observatories tried to replicate the finding. Some caught similar hints in their datasets, others saw nothing. The debate spread quietly through research circles. Was it real or just coincidence amplified by wishful thinking? The truth didn't matter yet. What mattered was that people were listening again to the noise, to each other, to the possibility that the universe still had secrets left to tell. When the conjunction period finally ended and telescopes reopened their eyes to the region near the Sun, every observatory on Earth pointed in the same direction. The air in control rooms felt electric, and their faint but undeniable Atlas reappeared. It was still moving exactly where predicted, but its brightness had changed. It was dimmer. That single detail reignited the mystery. Something had happened while it was hidden, something we couldn't see. The universe had blinked, and when it opened its eyes again, the picture wasn't quite the same. Now the question wasn't whether Atlas had survived the conjunction. It was what it had done during those weeks of silence. If you've ever wanted to see the universe the way scientists do, you can. You don't need a PhD, a lab coat, or access to a billion-dollar telescope. Everything you need is already online waiting for you to look up. The same tools used by NASA researchers to track interstellar objects like 3I Atlas are open to the public, and they're astonishing once you know where to find them. Start with NASA's HelioViewer. It's a free web portal that lets you view live images of the Sun captured by satellites like SOHO and the Solar Dynamics Observatory. You can watch the solar surface boil in real time, flares bursting thousands of miles high. Want to see what's happening near Atlas's orbital path? Just overlay the planetary grid and trace the area where it disappeared. That glowing wall of light is the curtain it hid behind. Next, visit the Minor Planet Center's database. It's updated constantly with the coordinates of every tracked object in the solar system. Search 3I Atlas, and you'll see its projected reappearance path. You can even download the orbital data and plot it yourself using open-source software like Stellarium or Celestia. It's like turning your computer into a virtual observatory. Then check out NASA's Eyes on Asteroids program. It's interactive, built in real 3D, and it lets you zoom from your living room all the way out to the edge of the solar system. You can follow Atlas's flight path as it moves past the inner planets, shrinking in brightness as it speeds toward the void. Watching that simulation in real time gives you a sense of scale that's impossible to describe. Every pixel represents millions of miles, every frame a piece of human curiosity stretching across space. Here's where it gets even cooler. You compare those sky maps with the Deep Space Network's live tracking feeds, the same radio telescopes that talk to the Voyager probes. When those massive antennas shift toward the Sun, they're often in the same direction where Atlas is hiding. That's the beauty of public data. It turns passive curiosity into participation. Try this tonight. Pull up NASA's HelioViewer, the Minor Planet Center, and Eyes on Asteroids at the same time. Watch how each system updates in perfect rhythm. When a new flare erupts on the Sun, the satellite images spike. When the Minor Planet Center logs a new position, the simulated trajectory shifts by a fraction of a degree. You're witnessing real-time science, the same heartbeat researchers rely on streaming directly to your screen. This is what makes the modern era of exploration so extraordinary. The frontier isn't locked behind institutions anymore. It's accessible to anyone who cares enough to look. You can literally track an interstellar visitor from your bedroom. You can see the sun that hides it, the stars it passes, and the data trail it leaves behind. And maybe that's the point of objects like Atlas. They're not just puzzles for scientists to solve, they're invitations for everyone else to wake up, to look up, and to remember that wonder doesn't belong to experts. It belongs to anyone willing to pay attention. Because when the next cosmic traveler arrives, and it will, you'll already know how to find it. You'll have the tools. You'll have the curiosity. All you'll need is the night. The night Atlas finally re-emerged from behind the sun, the world wasn't watching. There were no headlines, no live streams, no countdowns. Just a handful of astronomers huddled in dark observatories, waiting for confirmation that the interstellar visitor had survived its weeks of invisibility. And then one by one the notifications appeared. A faint dot of light had returned exactly where the equations said it would. Atlas was back, but it wasn't the same. The first thing they noticed was the brightness. It was dimmer by several magnitudes. That might not sound like much, but in astronomical terms, it's dramatic, like finding your flashlight on low battery after it's been shining at full power. Either Atlas had lost reflective material, or its surface had changed. Some called it evidence of outgassing, others suspected dust accumulation. But a few raised a more unsettling possibility that the object had altered itself somehow, as if reacting to its solar encounter. Every new reading deepened the riddle. Its spin rate seemed slightly slower, its thermal profile inconsistent. It was as though the sun had whispered something to it and it hadn't quite recovered from hearing it. When light finally hit its surface again, the spectrum revealed faint traces of molecules that hadn't been there before, complex carbon chains and sodium cyanide, the same chemicals found in the early building blocks of life. To the scientists, that discovery was both thrilling and unnerving. It didn't mean Atlas was alive. It didn't even mean it was special. But it did mean the universe still had surprises left to give. Every interstellar visitor we've found so far has challenged a different assumption. Oumuamua blurred the line between rock and technology. Borisov blurred the line between comet and chaos. And now Atlas was blurring the line between discrete chemistry and curiosity itself. The irony is that humanity almost missed it. During those same days, social media was fixated on the next big launch, the next AI breakthrough, the next trending controversy. While people stared at their screens, an object from another star quietly passed the sun and changed shape in the process. The universe doesn't wait for our attention spans to catch up. You might think that stories like this are for astronomers, but they're not. They're for anyone who's ever looked up at the night sky and wondered what's out there. Because what Atlas showed us isn't just about data, it's about humility. The fact that it reappeared, dimmer, altered, and chemically richer is a cosmic metaphor for us. Every time we vanish into our own distractions and emerge again, we're changed too. Maybe not visibly, but fundamentally. When the observatories logged their last readings of Atlas, the object was already racing toward the outer planets, fading fast. It would soon cross the line where even our largest telescopes could no longer track it. In a few weeks, it would be gone forever, just another myth written in light. But that final image, the dim traveler gliding back into the dark, carried a message. The universe isn't empty. It's full of fleeting encounters that refuse to fit our categories. And maybe that's what makes it beautiful. Because sometimes the most profound discoveries aren't the ones that answer questions, they're the ones that remind us how many we still have left to ask. Something invisible just tore through Earth. It didn't burn, it didn't crash, and it didn't even slow down. It passed through miles of rock, ocean, and atmosphere, as if the planet weren't there at all. And we only know it happened because deep beneath the Antarctic ice, a single sensor blinked. That sensor belongs to IceCube, the most remote observatory on Earth. It's not a telescope, at least, not in the way you imagine. It's a cubic kilometer of frozen clarity, embedded with more than 5,000 detectors. They're designed to catch the faint blue flashes that appear when a ghost particle, a neutrino, collides with an atom. That almost never happens. Neutrinos can pass through light years of matter untouched. They're the universe's quiet messengers, slipping through stars, planets, and even you billions of times every second. You'll never feel them, but they're there, streaming through your body right now. And on a night in early June, one of them carried a story. The flash it triggered was brighter and sharper than anything IceCube had seen in months. Energy levels pegged the meters at over 200 petaelectron volts, so high it could only have come from something catastrophic and unimaginably distant. For context, that's more energy in a single particle than any human-made collider has ever achieved. The event was instantly classified as a cosmic neutrino candidate. Within minutes, alerts went out to observatories across the world. NASA's Swift satellite slewed its instruments toward the region of sky from which the particle appeared to come. The Chandra X-ray Observatory followed. The coordinates pointed toward a faint, distant galaxy near the edge of our field of view, so far away its light had been traveling for hundreds of millions of years. Whatever caused that burst of energy might have already ceased to exist before life even emerged on Earth. Now here's where it gets weird. The timestamp of the detection lined up almost perfectly with another data anomaly, one logged by a neutrino detector in the Mediterranean called KM3net. Two independent sensors, half a world apart, catching the same signal within seconds of each other. That shouldn't happen. The odds are astronomical. The universe had whispered in stereo. Scientists spent days arguing about it. Some thought it was a coincidence, others suspected background noise. But as more data came in, the possibility grew harder to ignore. The trajectory analysis suggested the source wasn't random. It pointed back toward the same patch of sky where the interstellar object 3I Atlas had just emerged from solar conjunction. It was faint, unprovable, but haunting. Nobody was claiming a connection, but everyone was thinking it. The storylines of cosmic scale often rhyme before they meet. One object passes behind the sun, another particle arrives from deep space, and somewhere between them lies a mystery we don't yet have the language to describe. Here's the part that gives you chills. That neutrino traveled billions of light years, untouched, unstoppable, carrying a fragment of information across time itself. It entered Earth silently, left the same way, and in that moment we were part of its path, a planet that briefly intersected a cosmic message. You don't have to believe in omens to feel something when you hear that. Because every now and then the universe speaks, it just doesn't use words. When you hear the word particle, you probably think of something tiny, fragile, maybe even harmless. But neutrinos aren't fragile, they're unstoppable. Every second, trillions of them are streaming through you, through the floor beneath your feet, through the entire planet. They come from supernovae collapsing, stars, black holes, and the violent edges of galaxies. They're so small they barely exist, yet so energetic they carry the fingerprints of the universe's most extreme events. That's what makes IceCube so extraordinary. Imagine turning the entire planet into a listening device, and you'll start to understand how it works. The detectors buried in the Antarctic ice don't look for the particles themselves, they look for the rare moment when one finally hits something. When that happens, the collision creates a flash of blue light, a Cherenkov burst that ripples through the ice like a camera flash through fog. Detecting even one means catching a messenger that's been traveling for Billy. The discovery of that June neutrino wasn't just exciting, it was eerie. Because it arrived from nowhere visible. No gamma-ray bursts, no X-ray outbursts, no corresponding flare. It was as if something out there had released a single messenger without leaving any trace of its own existence. Astronomers scoured sky survey data for days looking for the smoking gun. Nothing. The sky was Q. That silence forced a new question: what kind of event leaves no light at all? One theory is that the particle came from the collision of invisible things, dark matter particles annihilating each other near a black hole's edge. Another suggests it came from an entirely new kind of astrophysical process, one that doesn't produce light, only neutrinos. Whatever the truth, it broke one of astronomy's oldest rules: every explosio. The eye. Across research labs, teams began to synchronize IceCube's data with that of its Mediterranean counterpart, KM3net. When they overlaid the detections, something fascinating emerged. The arrival angles of the neutrinos weren't random. They clustered loosely around the ecliptic plane, the same invisible sheet that holds the orbits of the planets, and coincidentally, the last known path of 3I Atlas. Nobody dared to call it a connection, but it didn't stop the speculation. The timing was uncanny. An interstellar object vanishes behind the sun, reappears altered, and within days, Earth records one of the most energetic neutrinos in history, coming from roughly the same direction. Maybe it's coincidence. Maybe it's a cosmic rhyme. Either way, it pushed scientists to think bigger. One astrophysicist from the University of Chicago described it this way: neutrinos are the universe's punctuation marks. Every time we detect one, it's like the cosmos taking a breath before it speaks again. That line stuck with people because it captured the emotion of the discovery. The data didn't just prove something, it made you feel something. And that's the heart of this mystery. Neutrinos are ghosts, but they're also storytellers. They remind us that even when the universe looks empty, it's full of motion, memory, and meaning we haven't learned to read yet. Every silent signal, every faint pulse beneath the noise, could be another sentence in a story still being written across time and space. So the next time you feel that quiet awe when looking at the night sky, remember this right now: something invisible might be passing through you, carrying a message from the other side of the cosmos. You'll never hear it, but that doesn't mean it isn't speaking. Across the frozen plain of Antarctica, the night never really ends, it just fades from black to blue. Inside IceCube's control station, a handful of scientists were still awake, long past their shifts, replaying the neutrino data over and over again. There was something about the signal that didn't fit. Its energy profile looked clean, but its timing was too perfect. Cosmic randomness isn't supposed to line up with human schedules. Yet this one had arrived exactly on the hour midnight universal time. That's not how nature usually behaves. At first, nobody wanted to say it out loud. The coincidence was almost embarrassing. But the more they examined the timestamp, the stranger it became. Not only had it arrived precisely on the hour, but the next two faint detections, much weaker but real, had followed at 1-hour intervals. It was as if something out there was pulsing deliberately, like a lighthouse beam from deep space. That discovery cracked open a dozen theories. Some believed it was just a statistical fluke, others suggested mechanical interference, but a small team decided to take it seriously. They began comparing IceCube's readings to other observatories' data, gamma-ray monitors, magnetometers, and even the Deep Space Network's background noise. To their shock, faint rhythmic spikes appeared across multiple systems. The pattern wasn't strong enough to call a signal, but it wasn't noise either. The media never heard about it. The results were too uncertain to publish, too strange to dismiss. Inside those labs, though, a new term started circulating quietly: the periodic anomaly. It wasn't a headline, it was a whisper. One researcher described it best: it's like hearing a heartbeat through static. The phrase caught on, echoing through emails and late-night video calls. Nobody claimed it was alien, but everyone admitted it was haunting. Because the rhythm didn't match any known cosmic process: no pulsar, no flare, no gravitational wave. It was slower, steadier, almost mechanical. As the data stacked up, one unsettling correlation began to form. The direction of the neutrino pulses roughly aligned with the same sector of sky where 3I Atlas had been just weeks earlier. Again, maybe coincidence, but maybe not. The patterns overlapped like two verses of a song written centuries apart. When word reached the team at NASA's Goddard Space Flight Center, they ran a simulation of the entire solar system, rewinding Atlas's trajectory and mapping it against the neutrino detections. The fit wasn't perfect, but it was close enough to make people uncomfortable. The idea that an interstellar object and a neutrino pulse might share a point of origin was wild, almost heretical. And yet nobody could disprove it. You can imagine the tension in that room: scientists who had spent their careers studying chaos now staring at a rhythm too deliberate to ignore. One of them finally broke the silence and said, "If this is natural, it's the most precise accident I've ever seen." Nobody laughed. And that's how the rumor began: the idea that maybe, just maybe, the neutrino pulse wasn't just a message from the universe, but a test. Not to see if we could hear it, but to see if we would notice. The first thing you should know is that the data isn't hidden. You can look at it yourself right now. IceCube publishes its neutrino detections in near real time. The list is long: numbers, timestamps, coordinates, but if you know what to look for, you'll see it. The pattern is still there. Here's how you can follow it. Go to IceCube's public events page. Each detection has a timestamp measured in universal time. Sort the entries for June 20th, 2025. You'll see 3 unusual neutrinos, all arriving within minutes of midnight, 1 hour apart. Their energy levels are extraordinary, above 200 petaelectron volts each. For comparison, the Large Hadron Collider operates at only a few trillion electron volts. These events weren't lab accidents. They were cosmic. Now pull up KM3-NETI's Mediterranean data feed for the same window. The detections there are weaker, but you'll find faint shadows of the same pattern: 3 small peaks that line up eerily well. 2 detectors, half a planet apart, listening to the same rhythm. That alone should make you pause. If you want to go deeper, open the NASA's HESARC database and search for X-ray or gamma-ray events around the same coordinates. You won't find any. That's the part that makes this so strange. The universe usually flashes in multiple wavelengths when it releases energy this powerful. But this time it stayed quiet. No light, no heat, just particles moving faster than anything we can build. Scientists are cautious about saying too much, but you don't have to be a physicist to feel the implications. Somewhere out there, something happened. Something powerful enough to send 3 particles across billions of light years, precisely timed, as if keeping tempo with an invisible metronome. And the direction they came from. You guessed it. Roughly the same region where the interstellar object 3I Atlas passed just weeks before. Coincidence or not, this is the moment when science becomes participation. You can track this story yourself. You can open the data, run your own analysis, and see if the rhythm holds. It's all there in public view. You don't need clearance. You just need curiosity. There's a certain beauty in that. For centuries, mysteries like this belonged to a handful of people with access to observatories and grants. Now anyone can join the search. You can be part of the investigation, not by believing, but by checking. Every person who downloads the data, every student who plots a timeline, every skeptic who looks at the noise and asks what if becomes a node in humanity's expanding nervous system. That's what the neutrino story is really about. It's not proof of anything. It's an invitation to look closer, to listen harder, to see whether we've been mistaking silence for nothingness. Because sometimes the universe hides its loudest messages in the quietest corners. So tonight, if you're curious, go look. The files are waiting, the numbers are still humming, and maybe, just maybe, the pattern will speak to you too. In the weeks after the neutrino anomaly, the silence that followed felt heavier than the discovery itself. The world didn't explode with headlines or conspiracy theories this time. It just waited. Research teams continued their analyses, quietly submitting papers that spoke in cautious language about anomalous correlation events and possible periodicity. But beneath the restraint was something more: emotional wonder mixed with unease. Because if those pulses weren't random, then somewhere out there the universe had just tapped on our shoulder. At IceCube, the staff rotated home as the austral winter deepened. Only a skeleton crew remained to maintain the detectors. The Antarctic night stretched endlessly, and the isolation made everything feel more surreal. Every time the aurora shimmered overhead, it looked like the sky itself was alive, rippling, whispering. One night, a technician stood outside the control dome, staring up at the curtain of light, and said quietly, "It looks like data made visible." He wasn't wrong. The same solar particles that dance through the atmosphere are cousins to the ghosts streaming through the ice beneath his feet. Thousands of miles away in Geneva, a data scientist named Nora was trying to model the neutrino pulses using machine learning. She fed the timing patterns into her algorithm, expecting chaos. Instead, it produced something uncanny, a rhythm that matched a geometric progression like music following an unseen score. Every new data point fell into harmony with the last. It didn't mean intelligence. It didn't even mean intent. But it suggested structure, and in the chaos of the cosmos, structure is its own kind of language. She shared her findings in a small virtual meeting with collaborators from NASA and the European Space Agency. One of them joked that if the pattern kept up, it would predict the next pulse for July 20th, exactly 1 month after the first. The call ended in laughter, but the timestamp stuck in everyone's mind. So they watched. Not officially, not on any mission schedule, just out of curiosity. And when the date came, the detectors were quiet all day until 2:35:959 Universal Time. A faint blip, a single neutrino, low energy but clean. Nobody said anything for a few minutes. They just stared at their screens, aware they were witnessing something impossible to classify. It wasn't dramatic, it wasn't world-ending. It was just one more piece of a pattern that shouldn't exist. That night, Nora wrote in her personal notes, "If this is natural, it's the most poetic form of chaos I've ever seen." There's something profoundly human about that reaction. We search for meaning, not because we're sure it's there, but because not searching feels worse. Whether the pulse is random or deliberate, whether it's physics or poetry, doesn't change the truth beneath it. The universe doesn't owe us answers. It only gives us patterns and asks if we're brave enough to listen. So maybe that's the point of all this. Not to find a message, but to learn how to hear one. Because when the cosmos hums a rhythm that touches two detectors on opposite sides of a planet, it's easy to dismiss it as coincidence. But maybe, just maybe, it's saying, you're not just observers, you're part of the song. If you want to understand what happens next, you have to step away from the observatories and look inward, because the next discovery wasn't made by machines. It was made by people who started noticing something strange in the patterns themselves. After the neutrino pulses, a quiet movement began online. It wasn't led by scientists or journalists, but by ordinary users scrolling through IceCube's public dashboard. They started comparing timestamps, overlaying the data with their own local experiences, power fluctuations, internet delays, even aurora sightings. It was harmless curiosity at first, the kind of thing that usually dissolves into conspiracy. But this time, the numbers aligned too neatly to dismiss. Reddit threads exploded with graphs and screenshots. Someone noticed that each neutrino pulse coincided with measurable spikes in geomagnetic activity, so small you wouldn't notice them without instruments, but real enough to appear in magnetometer logs. Others pointed out faint drops in satellite communication efficiency, milliseconds of lag that matched the timestamps exactly. Nobody could explain how a subatomic particle could affect a planet-wide network, but the coincidence pulled people in. Then came the strange part. Amateur astronomers reported brief distortions in star tracking software during the same window, small repeatable drifts that vanished as quickly as they appeared. They described it as though the night sky itself had glitched. That phrase, sky glitch, spread across social media like wildfire. Within days, mainstream outlets picked it up. The tone wasn't sensational, at least not yet. Most reporters treated it as an internet curiosity. Data nerds find hidden rhythm in neutrino pulse. But behind the headlines, something deeper was brewing. Scientists who'd spent years guarding their data found themselves watching the public make real discoveries. And they weren't wrong. When the logs were cross-referenced, the correlation between neutrino pulses and minor electromagnetic fluctuations held up. It wasn't causation, not yet, but it was enough to demand a closer look. That's when NASA's Deep Space Network quietly reanalyzed its telemetry archives. Hidden among weeks of routine spacecraft communication logs, they found a faint irregularity, tiny timing offsets between antennas thousands of miles apart. Normally those are corrected automatically, but when engineers checked the raw data, the pattern matched the neutrino pulses down to the second. The realization sent a chill through everyone involved. It meant the rhythm wasn't confined to IceCube or KM3net or even the planet. It was everywhere, subtle, global, and synchronized. A physicist at Caltech described it in an internal memo that later leaked. If this is interference, it's the most coordinated noise the universe has ever produced. And once that sentence hit the internet, the story escaped the labs completely. Forums, podcasts, and even late-night talk shows were suddenly buzzing about the heartbeat of the Earth. Most people laughed it off. Others didn't. Because deep down, whether you're a scientist or a skeptic, there's something primal about rhythm. When the cosmos keeps time, we feel it. Not because it's proof of anything, but because it sounds like us. Maybe that's what this whole sequence has been building toward. Not discovery, recognition. The realization that every signal we detect, every pulse we interpret, is filtered through the one thing we can't escape: our own heartbeat. As the heartbeat of the Earth spread online, it became something more than a story. It became a mirror. Every community interpreted it differently. Physicists saw data, mystics saw prophecy, musicians heard a tempo, engineers called it interference. And yet beneath all the arguments, one truth began to emerge. People were paying attention to the same thing at the same time, and that alone was historic. In Los Angeles, a composer named Eli ran the neutrino data through a synthesizer. He assigned each pulse to a note, stretched it into a sound wave, and layered it with low-frequency hums, sampled from magnetometer readings. The result was haunting, an ambient rhythm that seemed to breathe. When he uploaded it to SoundCloud under the title Signal 25, it went viral overnight. Listeners described feeling tingling in their chest and waves of calm, as if their bodies recognized something their minds couldn't explain. Psychologists at Stanford decided to study the phenomenon. They recruited volunteers, played them Eli's composition, and monitored brain activity. To their surprise, participants' heart rates and breathing patterns synchronized slightly to the pulse of the music, roughly one beat every 60 seconds. It wasn't hypnosis, it wasn't suggestion, it was resonance. Meanwhile, scientists at the European Space Agency tried to trace the origin of the electromagnetic disturbances tied to the neutrino pulses. Using satellites, they tracked the fluctuations and discovered something even stranger. The anomalies weren't random, they radiated outward in near-perfect concentric waves centered on Earth's core. The timing matched the neutrino detections within milliseconds. That finding turned the scientific conversation upside down. How could an event billions of light years away synchronize with something inside our planet? No model explained it. It wasn't seismic, it wasn't solar, and it definitely wasn't instrumental noise. It was as if the planet itself had responded. The story began showing up in unexpected places: TED Talks, documentaries, even sermons. Everyone wanted to claim the meaning. Some said it proved the Earth was conscious, others saw it as proof of divine architecture, and a few insisted it was a new form of communication waiting to be decoded. For the first time in decades, science and spirituality were staring at the same mystery from opposite sides of the glass. You might think it all sounds dramatic, but here's the quiet part: nobody could shake for the first time in modern history. Billions of people looked up, not out of fear, but curiosity. They weren't watching a celebrity or a disaster. They were watching data, a rhythm, something that might not even care that we noticed. And that realization that the universe could make us listen together without saying a word was more profound than any explanation. Whether the signal was cosmic, terrestrial, or purely coincidence didn't matter anymore. What mattered was that it happened, and for a brief, fragile moment, humanity heard the same beat. Because maybe that's how awareness begins, not with proof but with attention. A planet-wide pause, a collective inhale, the silence before we decide whether to speak back. Governments don't like mysteries they can't quantify. When the heartbeat story refused to fade, national research agencies began coordinating behind closed doors. It wasn't panic, it was protocol. Every unexplained global pattern eventually lands on someone's desk labeled potential security interest. Within weeks, quiet task forces formed at NASA, the European Space Agency, and the Chinese Academy of Sciences. Their job wasn't to explain the phenomenon, but to verify it. If it was real, they needed to know whether it posed a risk. The data didn't make that easy. The neutrino pulses, the electromagnetic fluctuations, the faint planetary echo all pointed to correlation without causation. Every variable could be coincidence, but coincidences that repeat start to look like intent, and that's what worried people. At Langley, analysts ran simulations trying to match the rhythm with known human infrastructure. Submarine communication systems, satellite constellations, even global power grids, nothing lined up. The timing was too clean, too regular. It didn't sync to atomic clocks, but it didn't drift either. It was running on something else, something steady enough to make even physicists uncomfortable. Meanwhile, in Geneva, CERN's supercomputers began crunching neutrino event models backward, looking for a hypothetical source. The results pointed to a region outside the ecliptic plane, somewhere beyond Pluto's orbit close to the Oort cloud. That alone shouldn't have been alarming. Space is full of random emission sources, but the model predicted that the signal, if it continued, would strengthen slightly every 30 days, as though orbitally modulated. That prediction put the next pulse on August 20th. Quietly, observatories prepared. Nobody wanted to admit they were waiting for a cosmic metronome, but they were. When the day arrived, IceCube and KM3NET recorded exactly what the model had predicted, a faint spike perfectly on time. But this one was different. The direction had shifted slightly, not from deep space, but from somewhere within our solar system. The data was incomplete, noisy, but one observatory in Chile managed to triangulate the angle. It pointed back toward the outer solar system, roughly along the trajectory of a fading object that had recently left the inner planets behind. 3I Atlas. The reaction was immediate disbelief. Correlation isn't causation, scientists repeated like a mantra. But in every conference call, every encrypted email, the subtext was clear. If Atlas was involved, then the story had just changed scale. You can imagine the dilemma. Do you announce that a possible interstellar object might be generating neutrino pulses? Or do you study it quietly and hope it stops before the public catches on again? Most chose the latter. But data has a way of leaking faster than truth. Within 48 hours, an anonymous dataset appeared on an independent physics forum, unlabeled, raw, and time-stamped. It showed the neutrino pulse arriving precisely 1 second before a faint gamma ray flicker in the same direction. 2 messengers, 1 heartbeat. If that was coincidence, it was the most poetic one in history. By late August, the question was no longer whether the pulses were real, but what they meant. The pattern had held for 3 cycles, each one a month apart, each one aligning a little closer with the projected course of 3I Atlas as it drifted toward the outer solar system. The odds of coincidence were now so low they could barely be calculated. What started as an oddity had become a message written in physics, a conversation we didn't start but might already be part of. NASA's Deep Space Network tried to isolate the next expected pulse before it arrived. They pointed multiple antennas across continents toward the predicted sector of sky and waited, logging every nanosecond of noise. When the moment came, September 20th, exactly midnight, Universal Time, the monitors flared. Not bright, not loud, just clear. The neutrino detectors on Earth confirmed another pulse, but this time, there was something new embedded within it. The energy wasn't uniform. Instead of one clean peak, the waveform showed 7 smaller spikes inside the main signal, spaced perfectly evenly apart. Some dismissed it as an instrumental artifact, but others noticed what it resembled: binary encoding. It wasn't language, not yet, but it was structure. The universe doesn't do structure for free. Within hours, the information leaked again. A graduate student in Madrid posted a screenshot of the waveform on social media with the caption, "If this is real, we're not alone in the conversation." It was shared millions of times before anyone could stop it. Suddenly, the story that governments had tried to contain became the biggest event on the planet. Late-night hosts joked about cosmic Morse code. Religious leaders called it the return of the divine voice. Data analysts live-streamed breakdowns of the pattern. News anchors spoke in the same half-whisper scientists used when they didn't yet understand what they were seeing. But behind the chaos, a few observatories stayed focused. They noticed something that everyone else missed. The waveform's 7 peaks weren't just evenly spaced in time. They matched, almost perfectly, the resonant frequencies of Earth's own magnetic field. That detail broke everything. If the signal was coincidence, it was an impossible one. If it wasn't, then someone or something had just sent us a rhythm written in the planet's own language. Overnight, the world divided itself into believers and skeptics. Some saw it as contact, others called it a data glitch, amplified by human imagination. Scientists begged for patience. Politicians demanded answers. The internet didn't wait for either. You could feel the change in the air, even if you didn't follow the news. Something had shifted in the way people looked at the night sky. It wasn't just curiosity anymore, it was expectation. For the first time in history, the world was listening together. Not for God, not for aliens, but for proof that somewhere in the silence, the universe might be aware of us. And as September faded into October, one question began to rise above all the noise. What if the next pulse doesn't come from out there? What if it comes from here? By October, something unprecedented was happening. The pulse didn't wait for detection, it began repeating early. Instruments around the world started registering low-level oscillations, roughly every 29.5 days, just enough to unsettle scientists who'd been measuring the timing with atomic precision. It was as if the rhythm was shifting, syncing itself to a new cycle, the lunar one. The moon had joined the song. The first to notice were radio astronomers in Australia, who found that the faint oscillations in Earth's magnetosphere grew slightly stronger when the moon was overhead. The effect was minuscule, far below the threshold of ordinary geomagnetic noise, but it was consistent. When the moon set, the signal faded. When it rose, it returned. Something was resonating across the space between worlds. Within a week, satellite magnetometers confirmed it. The pulse now carried a subtle modulation, like an echo bouncing between the Earth and the moon. No one could explain it, but everyone agreed it was new. Humanity had spent decades sending signals outward into space. Now something out there seemed to be sending a reflection back. NASA's Lunar Reconnaissance Orbiter was the first spacecraft to respond. Its sensors picked up microbursts of charged particles coinciding with each pulse, as if the moon's surface was momentarily electrified. The readings weren't dangerous, but they were impossible to ignore. They indicated active interaction, not passive reflection. In a secure video call between NASA, ESA, and JAXA, scientists, one researcher summed it up in a sentence that no one wanted to repeat in public. It's like the moon is answering. When the line leaked online hours later, it detonated. Overnight, the phrase, "the moon is answering," became the most searched term on the internet. Social media flooded with images of glowing lunar disks. Artists painted silver waves of light washing over the Earth, and even mainstream outlets started treating the event less like science and more like revelation. But beneath the noise, the data told a subtler story. The amplitude of the pulses wasn't increasing, they were stabilizing. The chaos was becoming order. The signal was evolving toward coherence. At the same time, linguists, mathematicians, and computer scientists began collaborating, informally analyzing the waveform's nested patterns. What they found deepened the mystery. The intervals between the subpulses followed the Fibonacci sequence. Nature's most universal code, spirals in shells, leaves galaxies, was now echoing in radio static between the Earth and the moon. If this was coincidence, it was the most beautiful one imaginable. If it wasn't, then something, whether cosmic, geological, or intentional, was weaving mathematics into the fabric of the sky. You could feel the mood of the planet changing. Governments stopped issuing denials. Telescopes pointed up every night, not to look for something, but to listen. Humanity had gone from observing the universe to waiting for it to speak again. And just before the next cycle's predicted pulse, a whisper ran through every observatory control room on Earth. What if this time, it's not a rhythm? Because in science, pattern is comfort. But when a pattern starts to change, it means the story isn't over, it's beginning. The pulse arrived early, not by minutes, but by hours. It wasn't supposed to happen until midnight yet. By late afternoon Universal Time, every magnetometer on the planet spiked at once. IceCube's detectors lit up with cascading flashes. KM3 Net's underwater arrays vibrated with electronic noise, and lunar orbiters went briefly offline. For the first time since the anomaly began, the signal didn't come from a single direction, it came from everywhere. What that means, no one can say for sure. It wasn't just neutrinos this time. The pulse rode on multiple carriers, electromagnetic, acoustic, and even gravitational faint ripples picked up by LIGO and Virgo within seconds of each other. That's not supposed to happen. Nothing produces perfectly synchronized signals across multiple forces of nature. Unless it's not a signal at all. Unless it's a state change. At first the public didn't notice. The internet lagged slightly, a few satellite streams glitched, and air traffic radar momentarily flickered. Nothing catastrophic, just enough to make technicians frown. But in observatories across the world, scientists were realizing the scope. Every sensor, every system, every frequency had registered the same spike in all-channel event. NASA's Deep Space Network issued a rare full-band alert, coordinating with ESA, JAXA, and private satellites. The early data suggested the source wasn't coming from deep space this time. It was originating within the Earth-Moon system itself, pulsing outward like a breathing wave. By nightfall, an eerie phenomenon spread. The aurora intensified across both hemispheres, blooming far beyond the polar zones. People in cities who had never seen northern lights looked up to find the sky shimmering green and violet. Photographers captured streaks of red that rippled in patterns, matching the known pulse intervals. It was beautiful and unsettling at the same time, order disguised as chaos. In Antarctica, IceCube's control team reported something even stranger. The detectors weren't just catching light anymore. They were recording rhythmic changes in the optical properties of the ice itself, as if the glacier were momentarily transparent and then opaque, breathing in light. And through it all, one word kept surfacing in the radio chatter of scientists and news anchors alike: coherence. Whatever this was, it wasn't random. The pulse had become a wave, and the wave had become a field. It was no longer just data. It was interaction. Then came the moment no one expected. The moon brightened, not enough to blind, but enough to be undeniable. Every telescope on Earth confirmed it, a measurable increase in lunar albedo, its reflectivity. For exactly 20 seconds, the moon shone slightly brighter, as if returning the signal that had reached it. When the light faded, so did the wave. The instruments fell silent. But in the following hours, something subtle lingered. Radio static across multiple frequencies hummed at a tone just above human hearing. Sensitive audio equipment recorded it as a soft, rising frequency, oscillating every 5 seconds. And within that oscillation, a pattern, a slow 7-beat rhythm, repeating endlessly. 7 peaks, the same count from the September pulse. Every scientist who saw that data felt it before they understood it. The signal wasn't over, it had only learned how to whisper. And somewhere between Earth and Moon, the space that used to be empty had just become alive with a sound too precise to be natural and too gentle to be hostile. The universe had stopped knocking, now it was speaking. When the wave ended, the world didn't exhale, it held its breath. Power grids stabilized, satellites resumed normal operation, and the aurora faded back to their polar homes. For a few hours, everything seemed ordinary again, but ordinary had changed. Every sensor on Earth now carried a faint echo in its calibration data. a residual tone that no algorithm could erase. It was as if the universe had left fingerprints on our instruments. In the days that followed, scientists began combing through the aftermath. Gravitational wave detectors reported micro-vibrations that continued for hours after the pulse, so faint they bordered on quantum noise. Radio telescopes, meanwhile, picked up a repeating tone hidden within background static. It wasn't a signal in any traditional sense. It didn't modulate, it didn't carry information. But its frequency matched the harmonic mean between Earth's magnetic resonance and the Moon's orbital period. Nature doesn't tune itself that precisely by accident. Engineers noticed it too. GPS systems started reporting infinitesimal drifts, fractions of a microsecond, that repeated every 7 beats. The Deep Space Network found that signal latency between its global antennas fluctuated rhythmically, as though space-time itself were breathing in sync with the pulse. But it was biologists who made the most unsettling observation. Within a week of the event, labs studying circadian rhythms in plants and animals began to report anomalies. Seedlings germinated faster. Lab mice displayed synchronized activity cycles despite being in isolated environments. Even human brainwave studies revealed faint entrainment, subtle synchronization, with a pattern repeating roughly every 5 seconds. Nobody could explain how an electromagnetic event could ripple into biology, but it was happening. The first person to say it out loud was an astrobiologist named Dr. Kwan during a live interview. When asked what the pulse meant, she hesitated and said, "Maybe it's not communication, maybe it's calibration." The phrase caught fire instantly. Cosmic calibration became the headline everywhere. Governments tried to calm the speculation, releasing joint statements that the event posed no danger. But public imagination had already outrun policy. Spiritual movements claimed the planet had been retuned. Physicists argued that we were witnessing a new kind of quantum resonance, an alignment between matter and vacuum energy. Social media filled with people recording the hum, convinced they could feel it through walls and metal. You might think it was all hysteria, but recordings taken from remote Antarctic stations confirmed that the tone was real, too low for human hearing, yet measurable as a faint, continuous oscillation that spanned the globe. At the same time, a few researchers noticed another strange detail. The amplitude of the hum seemed to spike slightly whenever humans gathered in large groups during concerts, protests, or global broadcasts. It was correlation, not proof, but unsettling all the same. For the first time, we weren't just observing a phenomenon, we were part of it. And maybe that was the revelation hidden inside the noise. The universe didn't reach out to tell us something. It tuned us to itself, to each other, to the fragile web of frequencies that keep existence from falling silent. Because the scariest possibility isn't that we're alone. It's that the cosmos just reminded us we never were. By the first week of November, the hum had become part of daily life. It wasn't audible to most people, but it was everywhere, woven into the background of machines, faintly visible in spectrograms, occasionally resonating through metal frames and glass panes like the world itself was quietly singing. Nobody could agree on whether it was still natural. What mattered was that it wouldn't stop. At first, researchers assumed it would decay with time like any other transient event, but it didn't. It held steady, unwavering, like a metronome too perfect to belong to chance. And then, something even stranger happened. The frequency began to drift, not randomly but upward, slowly, predictably. Satellite instruments detected the first rise in pitch. It wasn't much less than 1 Hz per week, but the consistency was flawless. Every system measuring the hum reported the same increase, synchronized to within fractions of a microsecond. When scientists plotted the frequency curve, the shape was unmistakable, an exponential climb. At the same time, deep-sea sensors started recording faint acoustic oscillations matching the same rhythm. The oceans had joined the chorus. Sonar buoys pinged in unison across thousands of miles, producing what one marine biologist described as a planet-sized heartbeat. Then came the human response. Meditation apps added the hum to their sound libraries. Ambient musicians sampled it. Hospitals noticed minor fluctuations in pacemaker telemetry coinciding with the rising frequency. Some doctors dismissed it as electromagnetic interference. Others called it entrainment, the human body subtly adapting to a new environmental rhythm. It was subtle but cumulative. Cities started reporting small but measurable drops in average heart rate variability during the hours when the hum peaked. Psychologists found that people exposed to recordings of the sound for long periods experienced vivid dreams, often describing light, rhythm, and waves. None of it was conclusive, but it all felt connected. Meanwhile, in a lab in Tokyo, researchers at the Institute for Quantum Communication discovered something that made even the skeptics nervous. Their entangled photon experiment, designed to test long-distance coherence, showed unexpected synchronization with the global hum. The probability of random alignment was effectively zero. The hum wasn't just physical, it was quantum. That realization changed everything. The phenomenon wasn't radiating from a single point anymore. It was emerging through the fabric of space itself, everywhere at once. The pulse had evolved into a field, a global resonance linking matter, energy, and consciousness in ways no one could model. When the United Nations finally convened an emergency assembly, the Secretary General's words captured what everyone already felt. For the first time in human history, the planet is sharing one rhythm. Whether it's physics or something more, we are all part of the same song. The speech was broadcast live to billions. For 90 seconds, as cameras rolled, microphones picked up a faint vibration that shouldn't have been there. The building itself was humming. And across the world, people heard the same thing, not with their ears, but with something deeper. The tone had risen just enough to cross into audibility, a low, soft resonance that brushed the edge of human perception. For the first time, the hum had a voice. And for the first time, we could hear it answer. The first recordings of the audible hum spread across the world within hours. Someone in Norway captured it on a smartphone during a snowfall. Someone in Kenya recorded it in a quiet field. Someone in Los Angeles swore they could feel it more than hear it, like the air itself was breathing. Every clip sounded different, filtered through landscapes, weather, and emotion, yet underneath them, all ran the same unmistakable rhythm. 7 slow pulses. At first, news outlets treated it like a curiosity. They played snippets on morning shows, let guests speculate, and laughed nervously when studio microphones picked it up on air. But the laughter didn't last. Within days, the hum had grown louder, still soft, but no longer deniable. It filled the edges of silence between traffic lights, under rainfall, beneath conversation. You could forget it for hours, but the moment you stopped talking, you'd hear it again. Psychologists called it a global phantom tone, a shared hallucination caused by expectation. But that theory collapsed when deaf communities began reporting that they could feel the vibration through walls and skin. It wasn't sound in the usual sense. It was pressure, subtle, rhythmic, all-encompassing. Then came the event that ended the debate. On November 20th, during a live broadcast from the International Space Station, astronauts reported hearing the hum inside their helmets. Space is silent and the ISS is shielded from external vibration. Yet the sound was there, transmitted through their own communication systems. It wasn't coming from outside, it was emerging from within. That was the moment humanity stopped calling it noise. The hum had crossed every boundary: atmosphere, biology, technology. It was no longer just the universe speaking, it was the universe singing through us. Around the same time, a research team at MIT finally decoded part of the waveform. The pattern of 7 peaks wasn't random. Each interval followed a geometric progression that, when translated into frequency ratios, produced the same sequence of notes used in ancient musical scales, the diatonic system that underlies most human music. In other words, the hum spoke our language before we invented it. Churches, temples, and mosques began holding synchronized vigils. Cities dimmed their lights. Pilots reported seeing faint waves of light across the stratosphere, pulsing in time with the rhythm. Even the animals responded. Whales altered their songs, birds changed migration patterns, and dogs howled at intervals so precise they matched atomic clocks. Governments could no longer frame it as anomaly. The United Nations reconvened not to investigate but to listen. Delegates from every country sat in a silent chamber in New York, microphones turned off, lights low, while the hum filled the room through no speaker at all. And when it faded, the Secretary General simply said, "We are not the audience, we are the instrument." You might think this would bring panic, but it didn't. Something deeper settled over the world, a quiet unity. For the first time in human history, 7 billion hearts seemed to beat to the same invisible metronome. It wasn't fear, it was recognition. Because after centuries of calling into the dark had finally called back. And this time it was in tune. When the hum finally stopped, it didn't fade, it resolved. One moment it was everywhere, the next it became a single pure note that hung in the air like the pause before dawn. Every seismograph, magnetometer, and audio sensor on Earth caught it, a tone so exact it fit perfectly between 2 musical intervals, neither major nor minor, neither happy nor sad, just balance. Then it vanished. The silence that followed felt heavier than sound. Satellites showed a momentary stillness in the ionosphere, as if the planet itself were catching its breath. For the first time, since the beginning of the phenomenon, there was nothing left to measure. No pulse, no vibration, no echo, just equilibrium. But humanity wasn't the same. Across cities and continents, people described the same sensation, a clarity, a lightness, a quiet understanding that words couldn't hold. Hospitals reported record lows in anxiety and cardiac events for 48 hours after the event. Social media feeds went uncharacteristically silent, not out of fear but reflection. In labs, scientists began to notice something subtle. The quantum noise that normally fills every measurement, those unpredictable fluctuations at the smallest scales, was reduced. Instruments that had never agreed before now showed identical readings, as if precision itself had improved. The universe for a brief instant had synchronized. Some called it coincidence, others called it grace. Astronomers looking outward found no repeating signal, no follow-up pulse, no cosmic flare. Atlas had drifted beyond detection, a speck swallowed by distance. The neutrino flux returned to background levels. The data was clean again, but that word clean no longer meant what it used to. The noise was gone, yet the world felt louder than ever with possibility. In the weeks that followed the phrase, after the tone began circulating in media and academia, it became shorthand for everything that had changed, the idea that history had quietly pivoted, not through destruction, but through resonance. Schools added it to curricula, artists painted it, poets used it as metaphor. Scientists refuse to define it. You might think such an event would divide humanity, but for once it didn't. Borders blurred, arguments softened, and collaboration became effortless in ways that analysts still can't explain. Maybe it was coincidence. Maybe it was calibration. Maybe it was just the reminder that connection is real and always has been. A year later, a group of school children in Chile recorded something remarkable while studying local seismic activity. Deep beneath the earth, miles below the crust, they found a faint, recurring vibration. It wasn't strong enough to be seismic, nor random enough to be noise. It was slow, one beat every few minutes, and steady. It matched the harmonic mean of the final tone. They didn't announce it to the world. They just smiled, printed the graph, and taped it to the classroom wall with a note written in marker. It's still there. Maybe it is. Maybe it always will be. Because if the universe was ever trying to tell us something, it might be this silence isn't the end of the song. It's the part where you realize you've been singing along the whole time.